now, and we are going to start off with the week one. I'm not sure if this is going to be according to it, but that's how DAIPODS is actually arranged. So we are going to delve straight into it. The call is being recorded for those that will come late. Usually we try to keep to time. They can watch it later. So we are starting. Today we are going to be handling these two, which is fundamental. That's the first the first module in DAIPODS. So now, like I said, we are taking everything from the scratch. We are assuming that all of you have actually, had this course or maybe used computer because it's safer that way, so that those that have already been through this particular session, it will be like it will serve as a refresher. But for those of us that are joining tech for the first time, is absolutely something that is beneficial, because you might not have this time again, where someone will take time to actually take you through the baby steps of this whole tech thing. So do it once and for all and forget about it, and then move on to other, higher tech career. So that's why we are doing that. So today, and we're going to delve straight into, what is a computer and everything about computer. That's this, which is fundamental. So, if we are to discuss computer, we know that computer today is equally referred to an electronic device. Yeah, we are going to talk about that electronic, like everything we've broken down, nothing confusing about the whole thing. But for the sake of the definition, computer is an electronic device that manipulates information or data. Sometimes data and information can be used interchangeably, but when we come to information, that's if you look at this, the third part of it is information management. You see the difference between data and information, but for now, don't worry about it. So this whole module is divided into four, and the way it is structured, we are taking it from the definition of the computer. So everything we are going to be doing in this particular module is stemming from the definition of computer. It is electronic device that has the ability to, number one, get. We are going to talk about get in this course. We are going to talk about processing. We are going to talk about storage. And we're going to talk about retrieval of information. When you begin to talk about your I/O, so whenever you hear I/O, something I/O, I simply means input and O simply means output. So I'm going to be touching some of these terms that you're going to be meeting, in your journey. So you already know that you can use computer to type documents, send email, play games, and everything. You can also use it to edit and create spreadsheets and make presentation and all that. Very good. Now, what really happens inside the system is what we're going to discuss in this, and that's what forms the basis of what digital literacy fundamental. Let us talk about the term computer. Okay, computer. The earliest use of computer is in the 17th century and is actually referred to the one who computes. Okay, somebody that does calculation and all that. A person performing mathematical calculation, is known as a computer. That was before this electrical device came, but because some people might be thinking, oh, computer at so point. I remember we talked about industrial revolution. I was specific about the electronic device. I will move from discovery of electronics to electronics device, and I promised that today I'm going to show you people the earliest version, continuing our journey from yesterday. So can I still be heard? Why am I seeing network thing here?
Yeah, I can hear you.
Okay. Yeah, I just saw one network error flash on my screen. Okay, so that's fine. So this man, Alan Turing, of course, most of the website now named after him, Turing.com, but that's not why we are here. He actually described a human computer as someone who is, okay, supposed to follow a fixed rule and has no authority to deviate from them in any detail. So Turing is known as the algorithm guy. You understand? In fact, the earliest form of artificial intelligence is trying to chat with a robot and you'll be able to kind of determine, there's a challenge to determine whether the robot is a human being or you're chatting with a human. So they call it Turing contest. But let's shift that aside, right? The first use of the word computer as a profession, like you have doctors, nurses, and everything, dates back to Harvard University. Okay. Um, that was when computer was officially used generally and publicly. Okay. They actually refer to as women. So all the guys here that are thinking that this tech thing belongs to you, sorry to burst your bubbles. The first computers were actually women. So in the 19th century, there were a group of people in Harvard University doing some experiments to calculate the number of stars and the galaxies and all that. Okay. Very, very prominent among them is Williamina Fleming. You can see her there standing. This is an ancient picture, okay, of them supervising a team of women. They call them computers. Okay, that's the essence of this particular slide at Harvard University Observatory. Okay, um, what they do, you're going to see what they do in the next slide. Let me just give you a little bit of history. You know, in the olden days, we have what we call wet plate photography. Wet plate photography, look at it. What you see here is the three steps that you take to take a photo. First of all, you spray it what we call colloid. Okay. After you dip it in silver nitrate, that second picture, you know, the colloid is actually to coat a glass. That thing the woman is holding there is a glass. You know, you spread it across it, then you soak it in what we call silver nitrate. And once you soak it into silver nitrate, it becomes sensitive to light. That's why the last picture there is in a dark room with red light. If you remember our film and everything, you know, if you use those Kodak Canon Canon cameras that used to put, they'll call it film. Film is actually, that name film is an advanced version of this glass because film is flexible and you can actually, you know, what's it called? You can store it, you can roll it. Yeah, I think you can roll it you know, into a particular container. You know, glass is very rigid. It can actually not be rolled. So, anyway, before we get to film, let me just explain. So, this particular thing, you know, you can see you have to take these three processes just to take a picture. Now, what this particular combination does is that once you expose it to light, okay, it captures, you know, the light reflection on it. You know, they call it negative, right? You remember the picture when you bring your picture, sorry, your film those days. If you open it, they go into a dark room. You know, I'm going to explain the principle of all this dark room that people used to do. So now, people kept, you know, like I said, the way you create, when you solve a problem, you create another one. So as of this point, this was like the latest technology, you know, photography and everything. So because you have to take this process every time you want to take a picture, it was not sustainable. People started looking for a way of doing it. Now they moved from what we call wet plate photography to dry plate photography. Now the same process, but you know, you have to take those processes and you know produce a piece of glass that is solid. You know, it still has all the colloid, it still has all the silver nitrate and everything. But this time around, you don't have to perform it over and over again. So they managed to find out a way of producing it in mass quantity. So you have a large, you know, empty plates, you know, that you can now use to take photos. Once you take photo, that plate takes the negative. You cannot reuse it again, you know. So it is easier to store. You now have more of them. You can see um this thing there, you can't really see it very well. So the picture you have here is a place where they store the plates. Instead of preparing one, once you want to take a single picture, you prepare another one, you prepare another one. So the picture you have then also is what we call observatory. Okay. Now, let me blow it up. This is observatory. Now, there is normal photography and there's one that you used to, kind of try to picture the galaxy. Okay. I'm coming to the women computer. That's where all this thing is going to end, right? So what happens is that look at how it is. You now see that there are some men operating, this massive, I'll call it it's not a camera, telescope, right? Now, what they do is you see them covering it with something that looks like a cloth, right? You see the first picture, you see the second picture. So what they are doing here is because the glass is light sensitive, they have to cover it in that dark place. So the cloth is usually black, it will not allow light to pass through it. So that once you open the aperture of this particular telescope, then it will capture the negative or whatever you are shooting. So also, if you remember the original pinhole camera, you remember they used to cover their head with black, kind of material. So you can see, I'm sure some of you have seen a picture like this. It's really relatable. I don't know how many of us are Gen Zs, but somehow, these are how the picture. So what they do is quite similar material, glass plates. They put it in the pinhole, open the aperture of the camera, it captures and they close it back. Okay, they will now go to a dark room and do what they call photo development, right? Now, some people might be asking, are we studying photo here? No, we are not. I just want you to understand what is going on. Now, these are the women computers in Harvard Observatory. Okay, so they kept on compiling. In fact, there is a museum now that have more than 500,000 of these plates, even though it's no longer used, but it's for studying purposes. They still look at it. So now, when you do that, you see what happens. This is the negative. So the dark spots are actually the stars and the galaxies and everything. You see, William and Fleming in 1888, this is the kind of thing that they did. So just to show you how it normally appears. So it's not as fanciful as what you have today. Okay. Now, at the end of the day, this is what they produced. So this is what the computing is all about, counting galaxies. Okay. So they check they what they do is there are a lot of uh, elements that are captured in the negative. So what they do is to try to differentiate the one that is a star and the one that is a galaxy. This is how the whole astronomy, when you hear astronomy, astronauts and everything, they actually started by observing, they can count the light. They try to, from observing, checking how they blink, they can they have a way of calculating the distance from. So all these things are going on. This is an example. This is a typical example of what they do. You see, they write on this whole thing. They put some numbers and everything. So this is actually the computer. Okay, as a human, these are women. That worked in observatory in Harvard University. So having said that, I want to equally, tell us that still talking about the computer, the way we know it today is an electronic device. But before the electronic device, there are mechanical computing methods of various forms. Okay. Fun fact, we're going to see some of the machine. You have differential machine here. I promised I was going to show you some of them. You see the earliest one. You have the abacus. You have the Napier bones. You have all of these. These are just mechanical. You can see there. None of this thing is driven by any electrical power. You can see the punch card there, the bottom left, which is the most popular, mechanical computer, the punch card, because what it does is it stores information. You see a sample of punch card there. The application of this technology was used to do design on fabric materials like rug. So what does it do? There are needles or pins that are mechanically operated. So anywhere that the thing should pierce is 1. Anywhere that it should not pierce is 0. So it has a way of being programmed and it produces a very beautiful design, like flowers and all that. So the punch card, the idea was actually extracted from that, and we were able to now use it to store information. So why this thing we are using to produce fabric, why can't you use this for storing information? So what happens is that you see the person operating the punch card is similar to the typewriter. So before the typewriter, there was a machine like this that perforates, cards. So you can see anywhere that there is hole, it is like one. Anywhere there is no is zero. So it has a way of storing information. And the disadvantage of this punch card that if you miss one, it means you have lost, the sequence of the information. It's going to be very difficult for you. So there are a lot of them. We are going to come to that, very soon. Now, let us fun facts, okay? How did we come from all these things to what we have the smartphones of today? Now, first of all, there is this man called Charles Babbage, okay? Um, the first computer was invented by Charles Babbage, but not built until 1991. He actually did this work in 1822. Of course, he was no longer alive, but the concept. So when people talk about who is the father of computer or something like that, even though it's arguable, but if you see Charles Babbage in any option, I think is the one that you choose, irrespective of whatever is there. But all this history sometimes is debatable and everything. But I'm telling you now, he's the one that, kind of invented the idea of analytical engine and differential engine. I actually showed it in the first slide. You see the analytical engine here, and you see the differential engine here. They actually used to make a lot of complicated calculations, stemming from the principle of abacus and all that. So it was mechanically driven. There is no electricity. It's for calculating, making just calculations, right? So you could see that as time goes on, there is this guy, Presper Eckert, okay, or Eckhart. I don't know the spelling, but look at, sorry, I don't know the pronunciation, but look at the spelling there. Is the one on the right and then John Markley on the left. So these guys use the principle of vacuum tube, right? And they produced the world first computer, electronic computer. We'll call it ENIAC. Right? I'm going to show you the full meaning of ENIAC very soon. Um, I think what they did was to actually adapt or adopt the principle of the punch card, 1 and 0, and say maybe we can use the vacuum tube to represent 1 and 0. So what is a vacuum tube, you might ask? A vacuum tube is simply a tube that is driven by electricity to either light up or goes. You just, okay, you can liken it to your bulb. Yes, I think that is easier way of describing a vacuum tube. It's like your bulb, it can come on and it can come off, right? So as time goes on, they begin to miniaturize this thing. The first smaller version of a computer is what we call Kenback 1. I'm just giving you a little bit of history, how we move from large machines to smaller one. The first was personal computer. That's, the credit goes to Kenback 1, invented before the first microprocessor. So please don't get overwhelmed by this term. See, everything will be broken down in this particular, we are going to break down what a microprocessor is. So everything, we are in the right place. So don't try to cram anything. So we're going to talk about microprocessor very soon. The machine did not have, have a one chip CPU, which is what we call microprocessor. But instead, it is based purely on small scale integration. Okay. And we're going to talk about small scale integration, large scale integration, right? So don't bother. So it was followed by Micro N, the world's first personal computer using microprocessor. See, the difference between Kenback 1 is this term, microprocessor. So sometimes you might see some of these things in history. They say, what's the first, the world first? ENIAC is not a personal computer. Okay, that's why I have to differentiate that, right? The one in the middle, ENIAC, is not a personal computer, right? But that's how this whole idea of computing with 1 and 0. We're going to do all these things today. So the first one that is small that one person can use is Kemba 1, but it was without a microprocessor. The first one you can give credit to that used the microprocessor is Micro N. It was the earliest commercial non-kit personal computer based on a microprocessor. Okay, so now having said that, let us look at the generations, right? This photo was taken from Site Bay because they've actually kind of they've been able to articulate it. So I have to give credit to them. They've put the figures there and everything. So I didn't need to reinvent the wheel. So let's go with this. Vacuum tube is known as the first generation computer. So if you're hearing generation of computers and all that, I'm going to explain to you the concept of this generation, the other generation, and everything. So before now, I used to cram this one, this one, this one. No. The idea of this is from 1946 to 1955, we stopped using the electromechanical devices and moved over to the vacuum tube. So the vacuum tube, does two things, right? It has two states, okay? Either it is on or it is off. Ladies and gentlemen, it is upon this particular principle that we have our computers today. Our computers still run on this principle, and that's why it's very important. You know where we are coming from. When we say the computer, it has a binary code of 1 and 0, right? So this is the first one, right? I'm going to show you at some point, okay, let me show you this, right? This is what a vacuum tube computer looks like. So the full meaning of ENIAC is electronic numerical integrator and computer. That's the first general purpose electronic computer. So don't mix it up. You see how large it is, right? All these things you are seeing, dot, 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 they are all vacuum tubes. So this particular computer is based on vacuum tube. The history is there on the right-hand side, but because I want you to really flow with this story. It is not complicated, right? Now, if I go to the next slide, you see what is happening here, right? This is exactly what we are talking about. At every point in time, okay, each of these bulbs can assume a state of either being on or being off. And because we have a lot of them, it means we can encode message, using different configuration. Some of us, sometimes when we do all these our topics in mathematics, we don't even know how it connects. You see, the idea of binary, I'm going to show you, see, these things are just the same thing. But the way we study them, we study maths and keep it. Then you go to physics, study electricity, keep it, you don't know about high voltage and low voltage and everything. Then on the computer, you cram the definition of computer, that they are all the same thing, right? Now, what you are experiencing here is different configuration. And in mathematics, you call it permutation, sometimes you call it combination, right? And if you have, let me start with a simple one. If you just have one bulb in your room, right? The bulb can either be off or on, meaning that you can send two messages, okay? And now, the second one is if you have two bulbs in your room, okay? How many configurations can we have, okay? Now, in this case, we will have possibility of 4 configurations. The first configuration is 2 of them will be off. That's one configuration. Okay, let me call one A and the other one B. Another configuration is that A will be on and B will be off. This is the second configuration. The third configuration is that B will be on and A will be off. That is the third configuration. Then the last configuration is both of them being on. You can see when we had only one bulb, we had 2 possibilities. Now that we have 2 bulbs, we have what? 4 possibilities. If I add another bulb, which is the third one, you can see how the thing keeps increasing I think it's n raised to power 2 or something like that, or 2 raised to power, and I can't remember, but we are going to come to the binary this thing very soon. So the more the bulbs that you add, please, whenever I talk about bulb, please imagine vacuum tube, which you are watching on the slide now. Okay, so if there are 4, if there are 5, if there are 6, so the more what you are having here, you can see there are many, meaning at some point it's going to do complex things that our human brain might not be able to do within the time that it's expected for it to happen, right? So that is it. You can see that's why the ENIAC will consume a lot of space. Like I said, in the history of civilization, when you solve one problem, you create another one. Fine and good. We are no longer using mechanical devices. Now we are using electronic devices. We are creating another problem. And what is the problem now? The problem now is that it consumes space. You can see what you are looking on the slide now. And remember, the vacuum tube itself produces heat. You understand? It's, unlike this our energy saving bulb that we have now, it produces heat. So imagine having this thing, and what you might even produce probably will be data that is just 4 MB, and you have filled the whole building with it. So you could see it creates another problem of space. You know, you need to be cooling it steady. And also remember, it's driven by electricity. So it consumes a lot of power, right? So it is expensive. And there's no way, you know, a private citizen can own some of the computer. That's why it is called first general purpose electronic computer. It is something that's owned by large organizations as at that point. And of course, what does it do? Even just calculation, it doesn't even play any news, just like we have today. So you can now see how powerful the smartphone you have today that is in your pocket is. Okay, so now, having said this, let us come to the second generation of the computer, right? So it is as a result of the problem I just mentioned. So because I need to tell this story the way it will be understood, right? How we move to the second generation of the computer, which is the transistors, is as a result of what I just mentioned. This first generation, fine, is good, is working, you know, it solves a problem, but it consumes space. It produces heat. It consumes electricity. Is there anything that we can do? So scientists kept researching, and the answer to that question is a transistor. Okay, a transistor is the principle behind even the computers we are using today, because it kind of replaces, transistor is more like a relay, is a switch, you understand, that can, you know, get signal, high voltage and low voltage. Okay, so when you transmit such a signal, it will be able to what? Record those signals. Now you can see in this case now, we no longer need to have what? A vacuum tube coming on and off. That's how transistor was the perfect replacement for a vacuum tube, because it consumes, it solves all the problem, right? Number one problem is space. Transistor is very small. The second problem is what? It consumes a lot of power. You understand? It solves that problem. Transistor does not consume as much power as the vacuum tube. The third one is heat. Transistor does not even produce so much heat, right? So you can see transistor became a, somehow vacuum tube died, right? Okay, how did you move to the third generation? I'm going to kind of demonstrate some of these things. The third generation is not really different from the second generation, but the third generation is called integrated circuits. That word integrated, if you check the dictionary meaning of integration, it means adding. Okay, for those that did engineering, he has something like differentiation. Differentiation is more like dividing. Integration is more like adding up. You understand? So integrated circuit is a circuit that combines a lot of transistors. So don't get it twisted. We are still moving on with our transistors. So integrated circuits, you know, you now have more transistors because probably there is, you know, there is desire and there is expectation to do more computation and everything, which transistor falls short of. Like I said, you know, it keeps on improving, okay? So that's the third generation. So we started having ICs. You hear IC, IC, IC. You know, my IC is burnt and everything. IC is integrated circuit. And these things that we're talking about is actually the fundamental of the brain of the computer, which we are likely going to see in this particular session called microprocessor. Now, the fourth generation is what we call large scale what? Integration. You see, it is still what? Integrated circuit, but it's now large scale, meaning that we are now talking of hundreds, thousands now. So what we are doing is simply improving on the configuration of the transistors. Okay. So at the end of the day, today, the fifth generation from 1980 to present, we now have what we call microprocessor. Microprocessor is simply what we call ultra large scale integration. You can see how this thing is not confusing. It is very simple to understand. It just depends on the way you look at it. So let me go to the next slide. I'm going to show you something. Okay. Now, look at this slide now. This is what I just described. Okay, this is what I just described. Initial of computing hardware, it started in 1960s. It marked by what? Conversion of vacuum tube to a solid state device, such as what? Transistors. That's the first paragraph there. And then it continued to what we call integrated circuits, and they call it computer on chip. So here, when you hear a chip manufacturing company like Motorola, you have Intel, even Apple has started manufacturing their chip. So chip. Please don't get it confused. Chip is simply integrated circuits. It can equally be referred to as what microprocessor as well. Around 1953 to 1959, discrete transistors started being considered sufficiently reliable and economical that they made further vacuum tube uncompetitive. So but vacuum tube died, right? Then we have this metal oxide semiconductor, MOS. Sometimes you hear something like CMOS. Well, we're going to see that in the hardware when we come to that. So we now have what we call large scale, integration technology, subsequently led to the development of semiconductors. Okay, now semiconductors were now used. You have PMP and MPN. Don't worry about that. We're going to talk about it. Started building memories mid to late 1960s, and then the microprocessor in the early 1970s. Yes, this led to what we call primary computer memory. Okay, what is primary computer memory? You are going to hear about RAM. Okay, we are now moving away from magnetic core memory devices to solid state static. Okay, solid state means it is not really spinning. Okay, now in order to bore you with this whole history, I want to let us go to something that is more relatable. Okay, your question will be, how does the transistor work? And this is how I want to demonstrate it. So transistor, look at the physical transistor shown there in the top left side. It has three, something like looks like a base, connector. So you have EBC. E is simply emitter. Emitter is something that produces signal, right? And what is it emitting? Electrons, right? B is the what we call base, and then C is the collector. So there's something that is emitting the electron, there's something that is collecting it. Now, how does the transistor replace the vacuum tube? That is what we want to explain in this particular slide. A transistor is a semiconductor, right? Device. Please start noting these names: semiconductor, chip, microprocessor. Nobody should confuse you. Nobody. So it's actually a semiconductor device used to amplify. Listen, note that word, amplify. Amplify is just to make large, make something big. Okay? Or switch electrical signals and power. So I told you just now that what is being emitted and what is being collected. So there is this device that can amplify that particular thing. Okay, so when it amplifies it, you're going to see it. It's called high states. You can see the picture there, the label below. You can see low states. Okay, So it is one of the basic building block of modern electronics, not just computer. And that's why this particular one is very important if you pay attention, right? So it is composed of semiconductor materials, okay, usually with at least three terminals for connection of any electric circuit. So there are three terminals there. If you look at the picture very well, you see something is on the left and something is on the right. So look at this now, okay? Now, if you have NPN, both of them will be serving as emitters in this case. At the end of the day, when they come to the middle, they'll cancel out. I hope you are seeing the arrow. That's what I'm demonstrating now, okay? They'll come to the middle and cancel out. You know, they kind of, what happened, okay, is that if you check the second one now, okay, this is what we call negative depletion layer. So nothing will happen. And that is the low state. Low state means that nothing happens. So that's the what you call zero in computer terms, right? Now let us go to the second one. You see this place now that I am emphasizing, something has happened. That's different between the first picture and the second picture. So the second picture is showing you that a positive charge has been applied to that particular plate, right? Instead of what you have in the first diagram, see what you are going to have now. Now, because of that, it eliminates the what? The depletion layer, meaning that nothing is canceling out. Then the direction of the electron is from the N-type plate, which is now referred to the emitter. There will be no need at this point for any vacuum. Sorry for the break in transmission. Can you hear me? I had a little network glitch here. Hello? Sorry, I need someone to confirm that I am audible before I continue. Okay, thank you. Yeah, I've seen the chat. All right, thank you. Um, please confirm that this is the slide that I didn't even know when my internet went off. Someone should just on the chat confirm that this is the slide that's or of the previous one. Okay, thank you. So yeah, so thank you very much. Now, so to explain what I'm saying, like you have the low and the high states, right? So please, whenever you hear computer 1 and 0, 1 and 0, binary means two things, 1 and 0, binary code and everything. I want you to begin to internalize some of these things in a non-confusing way. Okay, this is what changed the game. It is called transistor. It is transistor that brought about that idea of 1 and 0. So that is it. Like I said, there is on and off. Okay, on state is mean there's a semiconductor that allows a depletion layer, and then there is one like I said, that doesn't allow it. So let me go to the next slide to just kind of do demo. So this is a demo of what is happening, right? You can see at some point, the thing will start crossing, and it's called a high what? High state, which is on. On low states, nothing is happening until the depletion layer is eliminated. It will be flowing. So there's the emitter plate, and then there's a receiving plate. So this is just a demo to kind of visualize this whole thing. Now, having said that, okay, there are different ways that we can control this thing. Somebody might be asking, how is this simple idea of 1 and 0? How is it going to translate to the games that we play now, the codes that we write now, and all that? It is very simple. For you to begin to manipulate it, okay, because this is signal. We are not going to be doing only 1 and 0, off and on, and all that. It is logic gates, okay? There are ways, logic. Let me, first of all, I'm going to break everything down. The idea of logic is actually something that follows rules, okay? There are rules things have to follow. It has to follow a particular rule. You remember Charles Babbage defined a computer as a person, not as a person that is solving math, but as a person that follows rule without deviation from that rule. But that's by the way. Now, what actually manipulates these source signals for us to, create the complex computer that we have today is the logic gate. I'm going to explain all of them one after the other. Let me go to the first one. The first fundamental gate is a NOT. Not gate. Now, the NOT gate, if you see, just look at what is happening to that. You see red and lemon, okay? The lemon represents 1, while the red represents 0, okay? So the NOT gate has a signal, a triangle pointing towards from left to right, okay? And there will be a knob at the end of the triangle, and that knob signifies that it is going to give you opposite of, if you check what is happening, it is going to give you opposite of what is, if the input is 0, the output is going to be 1. If the output is 1, the input is going to be 0. So that is the idea of not. So the outcome is going to be not the the outcome is going to be not the input, right? So that's rule number 1. Okay. Now we have another one called OR gate. Okay. OR gate is no longer triangle. You can see the signals are changing a bit. So you have 2 inputs. You can see it is getting complex. It is only in the NOT gate that you have only 1 input. As we go further now, we are going to be seeing two inputs. Okay, even though the symbol is there on the right hand side, but I want to explain it now. See what you're going to have here. You're going to see that, in the OR gate, right, you have 2 possibilities. Remember, I just mentioned that you can have 2 bulbs in your room. Okay, one can be on and one can be off. Okay, then I'm going to come to and sorry, I did not skip. Yes, I see a comment. So now OR gate means if one is on, okay, whether the other one is off or on, let it pass. I'm going to give you an example here using real life, right? I like eating noodles, right? And I'm sending somebody to go and buy noodles for me. If you get to the shop, check whether they have Indomie. If they don't have Indomie, check whether they have what? Chiki, something like that. Okay? As far as you come back with Indomie, I am okay. That is a typical example of this particular logic. Okay? So it means that if they have Indomie, you can buy it. Forget about Chiki. But if they have If they don't have Indomie and they have Chiki Chiki, you buy the Chiki Chiki and forget about the Indomie. So this idea of buying is the outcome. I hope you are following the logic. Buy is the outcome. So either they have this or this, buy. Okay? The time you are going to come back with my money, listen, the instruction is that if they don't have Indomie and they don't have Chiki Chiki, please come back with my money. Don't buy. So there are two outcomes here, buy, and there's another outcome, don't buy. That is what is being demonstrated there. You can only buy if they have both, right? Or if they have any of them. So when it is 1, 1, the outcome is 1. When it's 0, 1, the outcome is 1. When it is 1, 0, the outcome is 1. Okay? So now, when it is 0, 0, the outcome is what? Absolutely 0. That's why I say if they don't have this and they don't have the other one, just come back. Okay? Now, for the person that's talking about the AND gate, so this is it. Please note these symbols, right? They are not really the same. Okay? They are not really the same. AND gate means the two inputs must be true before you take decision. Now, meaning that I'll give you a typical example to demonstrate this, right? It is only 1 when both of them is 1, 1. That's what it shows. If the first one is true and second one is true, that is the only way the outcome will be true. It is not like the OR gates. So a typical example to make it very, very simple to all of us is that I don't eat Indomie without egg. So I am sending somebody to go and buy, right? And I tell you, go and check if they have Indomie. Okay. Also check if they have egg. If they have Indomie and they don't have egg, carry my money and come back. If they have egg and they don't have Indomie, carry my money and come back. Okay. So with this, you can now say that the only reason why you will buy, remember, buy and not buy is our outcome. The only reason why you have to buy is when they have both Indomie and egg. That is why this is called AND gate. The two inputs must be 1 before the output is what? 1. Okay. Now the next one. So the next one is what we call NOR. Okay. Having explained these first 3, every other thing you're having now is a configuration. Okay. Now you are seeing that we have an OR gate. Okay. But you remember the first one I showed you is the NOT gate. Look at it up there. If you carry a NOT gate and choke at the end, right? What is going to happen is that whatever that is coming out of that OR gate, please change the outcome at the end. Simple. Remember, normally, if it is 1 that is coming, you change it. So it is simple. Don't cram anything. This is a simple thing. They just added N to the, there is OR gate. They are added N and make it NOR. NOR means chook this thing. Sorry, I'm using the word, but I think that's the best way you can understand it. Just add the what? The NOT gate at the end of the OR. It becomes NOR. So in that case also, that's what you call NOR, right? So you can see how simple this thing is. So when you add it now, the symbol is simply the NOR symbol with something like a knob at the end. Okay, so that's called NOR. So it is not going to be giving you opposite of the OR, right? That's what happens here. It's simply just changing. If you put a NOT gate at the end, it's going to be giving you opposite. Now, NAND. Again, remember we have AND. When you put N, it becomes NAND. NAND is simply take the AND gates and chook what? NOT gates at the end of it. When you do that, you are going to get a NAND gate. So the symbol is similar, but check again, there is a knob at the right-hand side of the NAND. Okay, so you can see that now you have this thing very well simple. Because when you go to mathematics, Boolean algebra, through statement, your head is already, they'll just give you a table, you cram. You're already confused. Okay? This thing is simple. It depends on the way it's broken down. Okay? Now, we have what we call the XOR and the, what we call also the XNOR, right? What you have here now is that it is going to be giving you, if you have, this is where the computer comes in now. If you have, okay, if you check it now, look at how the thing is represented. Okay, there is one, the one before the last one, which is XOR, and the one in the last. So you can see there's no knob in that one, and then the other one there's knob. So it's simply switching it. Okay, what this means is that if you check it there, it's telling you that if two of them are one, in fact, the only, okay, the only time, where you have zero is if two of them are the same. That is a better way of explaining it. XOR. XOR is saying if two of them are the same, if two of them are 0, 0, then output should be 1. If two of them are 1, 1, output should be 1. Any other thing, right? Forget about it. That is a very simple way of understanding it. I'll go again. If two of them are 0, 0, the output should be 1. If two of them are 1, 1, the output should be what? 1. Okay, so the only reason why the output should be 1 is when two of them are the same. So it's a bit different from the OR and the NAND and everything. You understand? Now, when you equally carry this knot, they cause problem. When you carry knots again and choke at the end, it switches everything. You understand? So that's why you now have X NOR. That whenever you have N, it means we are choking not that first one that we described. We are choking it at the end, which means now is that is now the opposite. The only time it can be true is only when one of them is true. If two of them are identical, please, outcome is 0. If it is 0, 0, the outcome is 0. If it is 1, 1, the outcome is what? 0. So we are now switching it now. So if it is 1, 0 or 0, 1, the outcome should be true. So this is it. Now, you can see how whatever is happening here is different configuration of how, the transistors. So what is happening here? The bulb is not coming anything on and off. There's no bulb here. It is the arrangement of the transistors. You can now see, what people do now is to kind of use this thing and build an integrated circuit to produce a particular thing. So please don't cry what is here. I'm just giving you an example. A washing machine, how the door opens, blah, 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 check temperature and everything. You can see different configuration of, they have put NAND, NOT and everything. I am not asking you to go and do this thing. I just want you to understand what is going on. These two decoders, well, you can see, so you can see this whole idea of 1 and 0, ladies and gentlemen, by the time you apply complex, logic gates, man, you are going to have multiple kinds of things, and that is what led to what we have today as integrated circuits. Now, ladies and gentlemen, we call it chip. So integrated circuit is called chip. You can see there are different versions. It has gone from one generation to another generation. Today, we are not going to be, for this particular session, when we go to the brain of the computer, the CPU, we are going to talk about configuration of integration. So for this slide, just know that the transistors has been actually rearranged in many different configurations, right? So it's made out of semiconductor material called the silicon, right? And the semiconductor now, remember, names are now coming in small. Semiconductor, silicon, chip. You can now see why Southern California is called Silicon Valley, because after the war, they actually invested all resources to kind of make this thing available for the public. Now every top tech companies, Apple, Google, Microsoft, Facebook, Meta, WhatsApp, Instagram, all of them have their headquarters in Silicon Valley. So that name Silicon is from, I think, is it Stanford University? A group of men came together and started researching on this. In fact, the real computing, the real war in the computing world is actually the chip. There was a time Motorola came. I don't want to go into all those things. Just let me just continue, Sha, before I deviate. So now the silicon, okay, inside the silicon, there are small electronic components called transistors. Are you following the story now? Have you seen, how what we call chip now? So there are a lot of transistors combined together, are formed within the silicon, and that's what we call chip. Okay, so now you can have it in various configurations, right? There's what they call surface mount and everything, but they can be extremely small, very, very reliable, right? And they perform this whole signal transmission at a very high speed. You can see everything here solves the problem of okay, someone said I wanted to hear the Motorola story. So the Motorola story about Apple. Apple came, they call it AIM. Apple, IBM, and Motorola. They wanted to, because Apple wanted a very efficient chip in their devices. So, and they wanted to fight Intel as of then. So they came together. They called them, what do they call it again? Is it a conglomerate? No. Consortium, yes, consortium. When different companies come together, they call it AIM. AIM. A stand for Apple, I stand for IBM, and M stand for Motorola. They do. At some point, the story is that at some point, Intel was too big for that competition, man. Intel, at the end of the day, the AIM crashed. The Apple that was even fighting Intel actually adopted Intel. I'm sure some of you that are using MacBook, if you check your MacBook, I see the sticker Intel inside, something like that. But Apple at some point, actually stepped up there again and said, hold on a minute. I think we can manufacture this chip. So as we speak today, Apple has their own factory manufacturing chips. So that's the short story. Let's continue. So the integrated circuits are compact electronics chip made up of what? Interconnected components, okay, that includes resistors, transistors, capacitors, and everything. So whenever you hear integrated circuits, you cannot, talk about integrated circuits without mentioning transistor. So it is different that the transistor they brought together, to build what we call the integrated circuits, which eventually is what we are using today in terms of microprocessor, no longer integrated circuits. So you can see this is more like just packing, because we cannot talk about this generation of computer without talking about packaging. So the way packaging did not start today. So the idea of packaging is actually how are these things configured? Okay. Sometimes, is it packaged in such a way that it's, sometimes when you get this thing, you see pin. Sometimes when you get them, you don't see pin. So if you see the one that has pin on the board where it's going to be mounted, you are expecting to have holes where those pins will perforate. And then on the other side, you now solder them. Okay, that's one configuration, one packaging. Another packaging is also you have pin, but it's not really pin that can perforate. It's a pin that on the other side there is a connector. All you need to do is just solder it on top of it. There's surface mount. So packaging became a thing because the way you package it should determine how small your chip is going to be and how efficient it's going to be and how many transistors can be packaged into one. All these things, of course, the research is still going on up to today. They are not stopping. There is competition. In fact, Huawei has entered the competition market. IBM is doing their own. Intel is doing their own. Now Apple has decided to go into the chip, so a lot of companies. So let us go to 1950s. The reason we are produced with only few transistors and diodes on one chip. Around 1960s, they introduced what they call bipolar what junction transistors. Okay, bipolar means two. You see them on two sides, right? Okay, no longer, I showed you the one that has three. Can I see the picture? Bipolar, bipolar. Is there any bipolar in this picture? There is. Okay, anyone you see just pin coming from one side is unipolar. If it's coming from the other side, it is bipolar. It's coming from the two sides. Okay, I think I will show you later. So let's not deviate. So in 1970s, we now have large scale, okay, and very large scale, okay, LSI and VLSI, allow for chip with tens of thousands. You see, we are moving from few to hundreds, tens of thousands, you can imagine. So when they tell you, say the computer now is very, very fast and efficient, you can understand where we are coming from and where we are today, okay? Now we are going from tens of thousands to even millions of this mounted on the chip, enabling the development of personal what computer. Now, if you can achieve this at that small scale, of course, you can have your laptop, of course, you can have your phone. You can see that the phone we have before now is improving in the size. It's becoming smaller, slimmer, and all that. Everything, all thanks to, you can give credit to the word called packaging and the evolution of the packaging. In 2000 and up to today, we have what we call ultra large, okay, integrated ULSI. We are talking about billions. So when you hear processor as the brain of the computer, which we are going to talk about today, so you can see the timeline there. So when I talk about the one that has hole and the one that does not have hole, forget about how I defined it. The correct name is what true hole package and surface mount package. But I had to describe it that way so that it will make sense to everybody. Now, when we talk about signal now, we have talked about how this integrated signal. So what is happening inside that integrated simple signal? Because no bulb is coming off or on. It is signal transmission now. And this signal is, that's why computer today is known as an electronic device. So as far as the signal transmission is concerned, computer can be broadly categorized into two. One is analog and the other one is digital. So when we define computers today, when you talk about 1 and 0, off and on, okay, this picture is needed for you to understand what we are talking about. When we talk about high voltage and low voltage, it's not like the high tension voltage. I'm talking about the one that supply lights, okay? We're talking about DC power. There's difference between AC. AC is alternating current, DC is direct current. So when you're talking about DC, you're talking about small power like your phone, and that's why you have charger, right? The what your charger does, if you plug your charger to light, remember what NEPA is supplying everybody is high voltage, AC. So that charger is what converts it to small. This you can convert 200. What normally comes is 220 to 240 volts to your devices like 12 volts or 5 volts, depending on how low your own this thing is simply called what? A converter or inverter, as the case may be. Yeah, the inverter does the same thing. It's just a matter of definition, but we're going to come to that later. That's why your laptop has what you people call power pack. That same thing your charger head, what you people call charger head, is doing for your phone, is the same thing your power pack is doing for your laptop. Man, if you supply AC to your laptop directly, it will fry. Trust me, you are supplying 220 volts to something that uses 5 volt or 12 volt, it will fry. That's why your keyboard in the church, your smaller devices and everything must have a power pack. What that power pack does is what you are plugging on the wall, what is coming out from that wall is AC, direct current that is coming from utility, NEPA and everything. So you can see when you talk about voltage and analog and everything, it's actually a continuous. You see the waves there, it's a continuous thing, right? But at some point, okay, the the um the particular configuration you are going to need for analog signals is going to be very difficult because it is what? Continuous, right? It is continuous. So you have to, I'm going to explain continuous when we come to sound. We are going to talk about how 1 and 0 transmit to sounds and everything, by the way, very soon. So, but look at this diagram beneath here now. You see that the second one, you see sharp edges, okay? So what is showing you is that the voltage is high. Remember, I showed you in transistor high state and low state. Either the voltage is high or it is low. So that high is 1, that low is 0. So that's what we call digital signal. And that's what we talk about: digitalization, digital technology. Digital is just that we are now talking about what something that can be represented with binary. I hope people are getting it. So when you have digital is something that can be represented with what? Binary. Okay. Now, having said this, there are other computers that are kind of, they combine the digital and analog. There are some things that will never change. For instance, the temperature of a room, right? You know, there's never a split of a second where temperature will disappear. Those that did engineering will know that differentiation is dy dx, and the explanation of that is limit of change of a particular parameter, while you know a small fraction of that parameter is tending to 0. It is not equal to 0. If you check, it is an arrow. Okay, just imagine a meter rule. Yeah, you break it into 2, you now have half. You take the other half, you break into 2, you have half. So you have quarter. If you keep on breaking that meter rule or wood or something, there will never be a time where the thing will disappear. Highest, you can grind it into dust, and that dust will still be measured in micro, like pico tiny particle. It will never be 0. A substance that is existing cannot disappear. It's not juju. In science, we don't understand that idea of, that's why he said dy dx, something changing with respect to something. That's the idea. So you can see, if we want to measure every single part of that, that's what we call continuous. So for instance, there is no split of milli or microsecond that temperature will disappear from the room. Temperature is continuous phenomenon. But if we are just having an AC or probably a sensor that wants to measure the temperature of a room, you cannot get a temperature that will keep on measuring temperature in microseconds. So it will be taking sample of it. That's what I'm trying to say. It can be every 60 milliseconds, right? That's why the concept, like I said, I'm going to be combining different concepts here. When you talk about frequency in waveform, it's number of times something is sampled per second. It can be a billion times per second. But do you have that power of something that will measure something in billion times within 1 second? No. So what we do now is to sample it, and that's how digital signal, at least sample it enough to still represent the actual thing. Okay, because temperature can change in seconds. I can sample it every second. It makes sense. Now sample it milli, small second. No. So that what you have now is a digital sensor installed in AC. If it is an automatic AC, okay, when you talk about building management system, it can switch. Switch means it can regulate the AC to the temperature of the room to come lower or higher. Okay, but that's by the way. That's the essence of this digital and analog. So let us delve into the digital computer as we know it today, right? The computer system is made up of two components: a hardware and a software. Like everything I've mentioned now, you'll be seeing hardware. We've not actually started touching software because everything about DAIPOD is software in various forms. Okay, so now for the software part of it, we are going to be talking about the system software and application software. Like I said, everything will be broken down now into small, small, tiny pieces so that nobody will be able to confuse anybody about this whole tech thing, right? So let's go on. Going to the hardware part of it, remember that I said this first lesson of DAIPOD is going to dwell on four things. When we define computer at the beginning, these four things came out: the get, the process, the store, and the retrieval. So what are we processing? What are we getting? Sorry. What are we processing? What are we storing? And what are we retrieving? Everything here is what we call IT, information technology. A technology that gets, process, stores, and retrieves. Nobody should confuse you about that. Okay? Now, depending on what you are getting, depending on what you are process, and depending on what you are saying, you now have different technology. Okay, so that's why I put a sample of that first slide at the top right hand side here. And also, the last slide I mentioned before one, you can see we have hardware and software. So let us go into it because this has a logical flow. I/O. I/O is input and output. So if you go to the last slide, you see the one I put in red that I am emphasizing here, right? Getting is how do you put information into that system? How do computers get information? Retrieving is how do I get information from the computer? Okay. I haven't mentioned that we're going to take two of them at the same time. Okay. I/O. So whenever you hear I/, we are going to be, these are the common terms you are going to be saying. Don't get confused. I just talking about input and what output. Okay. Before I go into the input and output, let us talk about you as a human, because this thing is very simple depending on the way the communication, is given out. How do you receive and give out information as a human? Let us even start from you. Yeah, you can hear me now using a device. If you think about it that way, it's going to be easy. And the sound that I'm producing in this lecture, I'm equally using a human device as well. So if you go into it, right, it is going to be easier for us to understand this. So we're going to talk about the central nervous system, because if you understand how this thing works, because you're a human being, you understand how, every other thing works. Okay, now the central nervous system is made up of two major components: the brain and the spinal cord. Okay, now the brain, as I'm talking about this thing, I'm going to move to the computer, right, very soon. What happens in the brain? You're going to talk about processor. This artificial intelligence, you are going to see how the brain played a major role in artificial neural network that gave rise to some of these things that we are, talking about today. And it is always good for you to understand this from the scratch. You know that we have a complex system. My leg is not attached to my brain. So the question is, how do you run when you hear a gunshot? Since your head is not, first of all, what heard the gunshot? Is it the brain? No, it is the ear. And we're talking about input. And then an output can be you jump the fence and to take your heels until you are sure that you are secure. All these things are working together because the transmission is from your brain to the spinal cord that connects to some of the muscles as well as the bone, and they have a way of coordinating. So let us talk about the brain. If you talk about the brain, okay, you have a place where we have memory, okay, they call it cerebrum. That's where you have the emotion, critical thinking, problem solving, and all that. Then, at the back of the cerebrum, you see the cerebellum. Of course, I'm just recapping this thing, Sha. Now, what does it do? It plays a major role in balance. It's not really what you are using to think, you know, motor control. So when I say, when you hear gunshots, first of all, your ear will hear it first. And then your brain will interpret, say, oh boy, now gunshot be this. So. And then somehow the cerebrum, will say, which muscle is needed? Is the muscle in the leg? Oh yeah, or more, it is time for us to what? To escape. Now, in the stem, you have what we call brain stem. It sits at the base of the brain, connecting the brain to the spinal cord. It is responsible for regulating processes like what? Breathing, blood pressure and all that. Now, let us talk about the spinal cord. Okay, it acts as the communication pathway between the brain and the rest of the body. Okay, so the rest of the body, that's why I said they are coordinating. Now, everything that you see here is still what happens in the computer. You can see the principles are not they're different. Now, apart from the central nervous system, we have what we call the peripheral nervous system. Okay, now the peripheral nervous system is divided into two: the somatic and autonomic. Okay, the somatic controls what we call voluntary. Okay, voluntary is the one like I just mentioned. Now, it's not like the peripheral nervous system is different from, sorry, it's not like they don't coordinate with central nervous system. No, they work together, right? So, like I said, when you hear gunshot from the right, the likely response, you are going to be heading towards the left. Okay? So, what happens is that when your brain receives it and then the brain interprets it and then it sends it to your spinal cord and everything, your brain will tell you the direction to turn. And that direction to turn, what is turning? It is your muscle and your skeleton. It's not the brain that is turning. What it is the brain that is telling it to turn, right? And then over now this side though, if you are going that side and you see people running away from that side, what do? You are confused. Either you turn back and you scatter. So now what you are seeing here is that at some point you now have what we call autonomic. Autonomic is the one automatic. Just call it automatic. If that one is going to make you remember it. Automatic is the one you cannot control, right? For instance, you are breathing. Some of you don't even know you are breathing now. Your blood is pumping. Some of you don't. It doesn't concern you. You understand? It no concern you until probably stroke come and try to affect that autonomic one. That so the brain controls what? The pumping of the blood and all those kind of things. But that one is something is involuntary. You cannot control them. You are breathing. I'm sure sometimes you even forget that you are breathing. So it's not you. Unlike the previous one that you are running, in this case, you are just breathing. In fact, sometimes you forget. Sometimes you don't know that your heart is pumping. There are other things like that. Okay, your lungs and everything, the oxygen and all those kind of things. Now, if you look at this thing, most of this nervous system does not communicate directly with the environment. There are what? Devices attached to your body that will communicate directly with the environment, and that is what I will refer to as human hardware in terms of input device. Your eyes, okay, is one. Use it to see. Your ears, use it to hear. Your nose, use it to perceive different kinds of light, smell, or odor or something. Your tongue, use it to taste. When you are licking ice cream and when you are chewing bitter leaf. Your skin, of course, nobody will tell you when you put your hand inside hot water, or when they flog you for school, So these are all the things we can consider an input device. Now, why is this important? Why am I saying this thing? Everything is coordinated, right? The eyes alone cannot work. Okay. Somebody said uric acid or join. Okay. If uric acid, of course, you still test it. I have not tested it before, and I don't wish to test it actually. So let us go to the hardware, right? For human beings, we have a way of getting information into our own computer. which is our system. If you think about it that way, this thing will become easy. Hardware includes the physical and tangible parts or component of the system which you can touch, you can feel. That's the hardware. Like, you can touch and you can feel hardware, but software you cannot feel and you cannot touch software, right? So you can touch your ear, you can touch your eyes, you can touch your this thing, but can anybody touch something that you are thinking inside your head? No. That's the software. Okay. Now, if you see somebody messing up, okay, your I don't know, depending on your own temperament, maybe your child or something, or your junior or younger brother do something, now there is a hardware that is working, that is your eye. The person is messing the room around, messing up the room, your eye is seeing it too. Somehow there's another device which is an output device, which is your hand. Depending on how your brain interprets it, there's a possibility that you are going to give the person a very, very, resounding beating. At that point now, you can see that there is an output and input. But the decision to beat the person, that's where we have this person is having anger issues or something. It is now the software. That anger issue, whether you're having anger issue or not having anger issue, whether you're going to beat or you're not beat, decision making cannot be touched. That's the software. That's where the RAM and the ROM is running inside your head. Somehow you believe that, I think better slap is going to, correct this situation. Another person, hey, just talk to the person and everything, depending on your own distance. So if you look at this, the hardware can often be categorized into what? Input, output, storage, and what? Processing. You see all this whole thing, processing and storage. Somebody can offend you and you say forgive and forget. Yes, we can forgive. I don't think we can actually forget. That is storage device. So show you people know. When somebody offends you and and like, you are storing it because you don't want that event to occur again. So you have it, they say, why are you keeping it in your heart? So all those things, where is your heart? So you have a silent how many gig, depending on how a lot of people can forgive easily, and they will actually forget. Okay, so it depends on how big it is and all that. So if you understand this whole IT thing like that, it's very simple and easy. So including all parts of the computer, we're going to talk about all these things. Now, please mark this word peripherals, because I'm going to be introducing this small, in a very mild way. Peripheral is something that you attach to a computer that, is not actual part of the physical hardware of that computer. I'll give you an example. Okay, what you call computer system, PC, personal computer. What you call personal computer, is just the computer itself. A computer system, please, ladies and gentlemen, can be complex. Immediately you took or you attach or you plug a printer to your laptop, that printer becomes part of that computer. They call it system. If you go back to human being, you have organ, you have tissue, you have system. Okay? So if you attach it, so anything that you can attach to that particular device is called peripherals. Okay? So you can see you have central nervous system and peripheral nervous system. So the peripheral nervous system is attached to central nervous system. So anything you can attach, be it modem that you use for your internet. Meanwhile, when I talk about attach, it must not be wired. There's what you call wireless and there's wired. Don't worry, there will be a time we're going to talk about protocols, wired protocols and wireless protocol, Wi-Fi, Bluetooth, and everything. This thing, we are going to break all these things down in such a way that it will not be confusing. But don't worry about that. This is not the time for it here. But what you need to focus on now is it a Bluetooth speaker? Is it a mouse? Is it a keyboard? Okay. Is it a scanner? Is it a whatever you attach that works with the system is a peripheral. You understand? So they are referred to as peripherals. Whether it's a flash drive, external hard drive, anything, a scanner and all that, you are attaching to the system. Once you attach it, what happens? Your system recognizes them. That is why you can print. Because if it is not part of the system, what will you do with it? You can't scan, you can't print, you can't transfer information to the flash drive, you can't do anything. So it is part of the system. Even screens, monitors. Okay, I have my own monitor, you can have your own monitor, but you can have a larger screen. You attach your monitor to that larger screen becomes part of it. What is it displaying? It's displaying what is coming out from your system. So please, this web peripheral should not confuse anybody from today onwards. So anything that you attach to your system that is not part of it is simply referred to as what? Peripherals. So why are we saying this thing? A lot of peripherals, okay, will be attached to the system either as an input device or as an output device. I hope we are taking notes. This is the reason why I mentioned it. Because not all input and output devices come originally with the device that you are talking about. Even your phone has Bluetooth earpods. We now have proliferation of AirPods now. You even have watch that works with the phone. I have all those things. So they are all become peripheral. They can either be attached with wire or wirelessly. Okay, now let's look at this. Of course, no, I can't exhaust, I just have to touch some of these things. How many things can we refer to as output device? The list goes on because as the world goes by today, things are changing. What we used to call keyboards now, we have touch screen. So what do you call it? So nobody should come and tell you that this is output device, this is input device, blah, blah, blah. My brother, leave am. The same phone, the same screen that we used to watch Netflix is the same screen I used to chat. So that screen now is both input and output device. So I don't want us to be rigid in our rationale about this whole thing. I want to make it simpler, right? Whatever you are using to input information into a system, whether you are using NFC card, we're going to come to data data capture machines, QR codes, and everything. So, but look at this slide for now. You can see the list. Please, this list is not exhaustive. That's my this thing here. So, graphics tablets, okay. We have trackball. Trackball is actually a bit, it's not outdated. There are some people that use trackball. It's like a rolling ball, that used to change movement of, maybe control the movement of a maybe game, or sometimes even they use it for military rockets and everything. So video capture hardware, of course, you have your camera, barcode reader. If you go to supermarket, when you buy something, you have something will scan. What is it doing? There is a number that is encoded in that barcode. It takes the number. That's how the system will be able to kind of get the information on that. You have your digital camera, MIDI board, gamepad, joystick, keyboard. Camera is repeated here. Sorry, I will change it. You have your microphone, you have your mouse, you have your scanner. Okay. You have your touchpad for those that do Photoshop in advanced this thing. If you have money, you can buy touchpad. It's like a pen, like a mouse pad or something you control. You have an electronic whiteboard currently used today. Of course, those that are watching super sports and the likes of what's it called, ESPN and all that, they use it to, control, yeah, analysis of the match and everything. Optical character recognition, optical magnetic recognition. You have pen input, you have punch cards reader, you have magnetic ink character reader, magnetic tape drive, and all that. For output device, of course, output is how do we retrieve information. You can watch it on the screen, whether LCD, LED. You can equally print it out. You can print it with a plotter, microfiche, the projector, the headphone, which you use to kind of listen to your sound. the computer output microfilm, you have the speakers, you have visual display unit film. But some devices, like I said, have both what input and output. I see a lot of people raising hand. Please, I'm going to give the last part of the class for question and answers. Please, just note your question. Then we have both input and output touch screen. Okay. Why is it input? I just explained that you watch video, you still use it to chat. So you still use it to input. It still serves as your keyboard, you know. Modem, of course, you have upload and download. So it is both input and output. Network card, the same thing that modem does. Audio card, sound card for those that are sound engineers in churches, you know what it does. Headset, of course, with your earpod now, it has microphone as well, which you can speak into. And the microphone acts as input device, while the speaker of the earpiece acts as output device. So we have fax. Fax, of course, you can send and receive messages. Fax is actually outdated. So we are going to round up so that tomorrow we can look at CPU, because we have talked about get and retrieve. That's what we just finished now. Tomorrow we'll talk about CPU and storage, and we have concluded this. I'll move over to the second letter A. So, but let me see what we can do now so that we don't really start, you know, from beginning. Yeah. So the central processing unit. Now we are now coming to the computer itself, right? Central processing unit is where you have your microprocessor. No need trying to explain. I've actually talked about how we move from transistors to integrated circuit microprocessor. What actually happens in a microprocessor? That is what we call central processing unit. And that is the brain of the system. There's no system without the central processing unit, right? Just like we have brain, it is the brain that is controlling every part of us, right? So the central processing unit carries out all the important functions of the computer. It receives instruction from both the hardware, okay, and active software, and produces an output accordingly. Generally, CPU has 3 components. I'm going to use this and end today, right? In the brain of the system, 3 things happen, right? There is ALU. In fact, that is the handshake between the hardware and the software. You see, when you narrow down the system, what is this magic? The magic about the system. In fact, if you narrow down the central processing unit, it is the ALU. That is the actual computer, because it does a lot of computation, right? ALU is called arithmetic logic unit. All the logic that we talked about, logic gate, no matter how complex it is, the ALU is able to what? Resolve it. And that is how we are where we are today. We have supercomputers and everything with different configuration of ALU. You can see you have your input there, we have talked about it. You have your output, and then you have your primary memory and secondary memory. The primary memory is the one inside that box that is close to the ALU. Okay. The secondary memory is the one that is outside. They call it the main memory of the system. Primary memory and the main memory. Main memory is secondary memory. Secondary memory is used to store data permanently, like your flash, unless you delete it, by the way. Flash drive is not hard drive, but that's the next topic in this particular module. So let's leave storage for now. Let's focus on what is happening inside that box. So 3 things: ALU, control unit, and memory. Memory in this case, that bullet point you are seeing there, is talking about primary memory, not secondary memory, please. Okay? Okay, let's go through them one after the other. It is called random access memory. So when you are buying anything today, you need to check how large the memory is. Please don't buy anything less than 8 gig RAM. It won't function in the world of today. 4 try, but I think you should go for 8. Both systems, okay, and okay, phone, maybe 4 can work on phone, but do you know the reason? This is the reason. This is actually the part of the system that is working directly with the brain. That is the ALU. That's why it is there, right? The reason is it needs to be large enough to store temporarily information that the ALU can easily fetch and equally store, some memory units. It can fetch memory units from it and equally store memory units. So it easily communicates. So if it is not large enough, your system will be hanging. That's the thing. If you have a fast processor, you understand. That's why a lot of times some people that are learning, you see, this whole DAIPODS itself isn't going to, like, it's important for everyday this thing. If your laptop is, for instance, 4 gig RAM, and your track, you went and choose, what's it called? Mobile app device, mobile app, mobile app development. All of a sudden, you are advised to download Android Studio. You download Android Studio, Qualcomm, nothing they work again. Your system is freezing. The reason is your RAM is not, capable of handling a lot of work, because that's where the active information is stored and retrieved. Active, not passive. That's why it's called primary. That is where the information is fetched. We are going to talk about the I cycle. Okay. Now, the second thing there is the control unit. The control unit coordinates the function of all parts of the computer. Okay. It does not involve, it's not involved in the processing or storing data. So it's like a bouncer. It's not interested in the party, but it controls what goes on in the party. The reason is that if there are no bouncers and ushers and everything, the party will be very chaotic, because some people will enter VIP when they're not supposed to enter the VIP. So they ensure order. Okay, if you use the bouncer concept, you understand what the control unit does. It tries to, it's like a personal assistant to the what ALU. If you are trying to wash a car and the bucket sounds like the memory where you fetch water to wash the car, the act of washing the car with your hand is what the ALU does, but fetching water, it's controlled. You don't pour water anyhow. In fact, if you have somebody that is helping you, if the person is not careful, the person will be pouring you water instead of pouring water on the car. You are the one that's okay, no, pour here, pour here. So it has to be poured in a controlled way, in such a way that because you can actually sprinkle water on the person that is washing the car if you don't do it. So the memory, okay, has the control unit to help it to organize information. We're going to talk about multi-threading, multi-processing and all that. Organize it in such a way that it doesn't crash the ALU. Okay, but that doesn't mean that, of course, bouncer, there's a way people will come inside and have a stampede. The bouncer is useless. Okay. Somebody is talking about VM1. Don't worry, we're going to come to virtual machines very soon. So the ALU, okay, is the portion of the CPU which performs the arithmetical and logical operation. That's the computer itself. Computer is an act of calculating and computing, right? The arithmetic function includes addition, subtraction, multiplication, division, other logical function. Of course, I've mentioned logical functions is referring to all the logical gates that I mentioned and all that. Okay. So what we are going to talk about in the next class, I need to have some time to take question, is we are going to talk about some of the things in the hardware and how they are coordinated. We have computer bus, okay? If I continue, it's going to get clogged up, right? So what I'm going to do now, I'm going to stop here and I'm going to recap, right? I'm going to recap and then we take questions once it is, it's almost, hold on. All right, so I'm going to rush through this. All right, so we started by defining what a computer is. For those that are just joining us, you can see it has ability, electronic device, by the way. For those, I think people now understand why this electronic is very, very important in this definition. Electronic device that has ability to what, get, process, store, and retrieve information. All right. So we may uh okay, I think that's for this. So data is at the center of it all. And we talked about the term computer being referred to as somebody that computes, even though Alan Turing has the idea that computer is someone that follows instruction. That's fine. But the official use of the term computer as a profession is used for women that actually does the computing work at Harvard Observatory when they were studying the galaxies and the stars. So what do they do? Of course, we talked about the photography and everything. We have wet plate photography where you prepare it with liquid. That's why it's called wet. At some point, it is not sustainable because you have to do it over and over again for you to just capture image. They actually devised a way of making it dry, so you can have a lot of them and use them. So they are used in this. This is an example of an observatory. You see that thing that looks like a dome is just to protect light from entering the place. Then you have a telescope, and what you are going to do is you put the glass plates, okay, that is covered with collodion, collodion. That's this thing, and then is immersed in silver nitrate, which makes it photosensitive. That's why it's always done in a dark room. So this is the thing. You can see the black clothes there at the end of the telescope, and then the plate is put there, and then it's open for the aperture. The aperture is open and it captures this thing. So of course, it is equally something that we are familiar with in the pinhole camera that heralded the whole idea of photography. So what we are saying is that these women actually get these things, and this is like negative. They call it negative. The white is supposed to be dark, and the dark is supposed to be white. So what you are seeing dark is actually shining stars and galaxies and stuff like that. At the end of the day, you see the computing. What they do is counting galaxies, how they blink, and how long it takes us to see the blinking. And they're able to use it to calculate how far something is. So this is the first computing, as a career. And the women that does this are computers. This is one. This is actually a real life result, that was archived. See, that's what they sit down and do all day. And I talked about before the electronic computers, there were mechanical methods of doing different kinds of calculation. And the guy, Charles Babbage, actually invented what we call the analytical engine and the difference engine, all mechanical devices until we went to ENIAC. Okay, ENIAC is the world first electronic device. It uses vacuum tube, as I mentioned. Then Kembat is the world's first personal computer without a processor, without a microprocessor, while the Micro N is the first world personal computer that uses a microprocessor. We talked about different generations of computer systems, and we talked about how vacuum tube is used to represent information, 1 and 0. We move to transistors. I'm going to show you how transistors work, and then we move from integrating few transistors to billions of transistors, where we are now calling it ultra large scale integration. So this is ENIAC. This is operation of ENIAC, on and off, representing different information. And we talked about evolution. I think this has been well explained. This is when we talked about how transistor works, the low states and the high states, off and on, 1 and 0. So you can see low state is actually, you have an emitter, you have a collector. At the same time, you have what we call the negative depletion layer, where the electrons are coming from both plates, kind of nullifies or neutralizes each other at the middle. But in this, when you apply, so that application is done in the second part. You see where you apply a positive charge and then the depletion layer disappears. So the thing is now moving in one direction from the emission for the emitter to the collector, and that is what we call high. So with this now, we no longer need what? We no longer need light to come. So somehow vacuum tube died. Nobody's using vacuum tube again. So this is more of the illustration, that shows how at some point when this thing disappears, the electron can now flow across. Having said that, we went to logic gates. We talk about NOT. When the input is 0, the output is 1. When the output is 1, the input is 0. This is the simplest logic gate because it has only one input and one output. Until we went to OR, we have two inputs, okay? Whenever any of them is true, the output will be true. It is only false when both of them are false. I talked about and two of them must be true before you have a true output. If one is false, then you can never have a true output. Then we talked about NOR. NOR is when you combine the OR gate and the NOT gate. We talk about NAND, when you combine the AND gates and the NOT gates. And then we talked about XOR and NOR. We talked about how these things can be used in the real life, using washing machine and this decoder as an example. Integrated circuits, of course, we see how we move. We now know what we call chip, transistors, mounted in a silicon, and they have solved all the problems that was brought about by the vacuum tube. We have different packaging. Two major categories of packaging is what? Through hole package and surface mount package. So having said that, we now have digital and analog computer. I explain what digital computer is. I explain analog computer. And of course, when we talk about today's computing, we are talking about digital, which is 1 and 0 representation. So to put context to it, we now moved into the hardware part of it, where we brought back how we started getting and retrieving information. We now talked about input and output. As human beings, we have our own hardware, right? That is imputed on us from birth. Now we talked about the hardware. We listed some of them, hardware inputs and outputs, and we ventured into the processing. And with that, we defined the three major components of the processing. We have the memory, we have the control unit, and the ALU. Memory is what we call primary memory, which is the RAM, random access memory. We are going to break this thing down in the next listing. So this is just the tip of the iceberg for central processing unit. In the next class, we are going to talk about it. The control unit, of course, is coordinates the functional activity, and ALU is where the main calculation goes on. So from tomorrow, we are going to be talking about computer buses. You can see how everything works. We're going to talk about information data processing. We're going to talk about, the text, how text is converted. We're going to talk about the color. We're going to talk about the image. We're going to talk about the sound. We're going to talk about the what we call e-cycle, which is execution cycle, talking about CPU specs and all that, so that you understand when they talk about core this one, core the other one. All these things we'll talk about tomorrow. So this is 3:48. We're going to leave the last 10 minutes or thereabouts for probably questions and answers. Ladies and gentlemen, this marks the end of the class today. Thank you.
Okay, thank you very much, Lawrence. Wow, the chat is on fire. Guys, I hope you're how is your head, guys? Do you guys need a chilled drink? Like need to get some ice block and just place on the head. Okay, so yeah, let's take questions, right? Does anybody have a question? The next 10 minutes we should be out of here. If you have a question, please just raise your hand and we'll attend to that quickly. Okay. Mary Jane, go ahead with your question. Yeah, Mary Jane, you can ask your question.
Okay. Good afternoon, sir. Thank you very much for this section. So my question is, the one you were talking about generations of computers, I wanted to know if it has anything to do with computer generation that we normally see as system information, does it have anything to do with that?
Can you give me an example?
Like when you say this computer is first generation, it's
Oh, no. Okay. I understand. So, yeah, I understand. So when you have some of those, this thing is actually company based, right? Code house, the way we do code camp 5.0. This is our own fifth generation code camp. So yeah, when you see some of those things is actually based on the configuration, but generally the computer um, history, yes, they are definitely what I just talked about today. But when you come to companies, you understand, it's actually based on their own nomenclature, and I think CodeCamp is a very very good example of it. So we are in CodeCamp generation 5. So yeah, that's the answer to your question. So sometimes companies see different things, coming in. They have a way of putting their own version 1, version 2, version 3. So please don't confuse it with the generation first computer generation. Thank you.
okay. Thank you, sir.
Okay, I'm sure that was answered. Any other question? Oh,
Yeah. Also, another place you see the generation also, the G in 2G, 3G, 4G, 5G. That G equally means generation. So you have first generation. You can see another use of it also. So don't confuse it. 2G is second generation, 3G is third generation, 4G, 5 generation, 5G now that we're talking about. In fact, there is already a research for 6G, man. This guy's working person. They say GT is going to be downloading 3 terabytes per second when that one comes out. But it's fine. Yeah, it's all for learning. So that's another place to see G. Yeah.
okay. Yeah, I believe that question has been answered. Do we have any other question? Okay, so well, since we don't have any, so someone is asking how if the class is recorded. Yes, so yeah, the DAIPODS class is recorded. In fact, all classes in CodeCamp are recorded, and you can find that on our YouTube channel. Okay, Salam, you have a question. Okay, go ahead quickly. I think that will probably be the last question we'll take. Sadiq Salam, you can go ahead with your question.
Hello, good evening.
Yes, good evening.
Good afternoon, also.
Good afternoon also.
Thank you for the presentation. It was a very good one. But at the beginning, there's a place I didn't get it right. That's where you mentioned types of computer. First, you said that when according to the pictorial picture, I mean the pictorial presentation, you gave us analog and digital. But when you get to the note, it was analog, analog, digital, and hybrid. Please, can you explain that hybrid of the thing now? That's where I'm getting confused.
All right. Yeah, it's fine. Just a minute. So look at it here. Okay, so when you talk about analog, when analog is there are signals. Okay, let me read it out. Okay, analog computers are designed to process analog data. Analog data is a continuous data that changes continuously and cannot have discrete value, such as speed. You have temperature, pressure, current. At every, like, let me just use temperature for instance. The room that you are in now, there's a temperature in that room. And there will never be a time that temperature will cease to exist, unless probably it's a vacuum, right? So in that room, that parameter, temperature, can be measured every minute. Do you agree with me? Please unmute. Like I want it to be interactive. Sadiq,
Yeah, I agree with you.
can you hear? So
I can
you know
hear
that
you.
that temperature can equally, you know that temperature can equally be measured after five minutes and be recorded.
Sure, sir. Yes, sir.
So in between the 5 minutes that I recording temperature, does it mean that temperature does not exist in the room?
Sure, it exists.
Now, even if you are measuring it every 5 seconds, in between the 5 seconds, there is still temperature. Even if you are measuring it
Sure.
2 times in a second, millisecond, microsecond, and everything, you see, temperature is a continuous. So when I talk about continuous analog parameter, you understand? It does not, like, you cannot say, oh, there's a time. It does not. It's continuous. What we do in real life is to make it simpler for ourselves, okay, and discretize it and make it digital. Digital now is the example I just gave you. If I decide to be measuring that temperature, I have a device in the room, a thermometer in that room that's going to be measuring temperature every second. It has digitized it. I can record the temperature, every second. So it's like a point. I'm now having like a point data every second, another point, every second, another point, every second, another point. I have digitized this, but the parameter I'm measuring in itself is actually analog. So there are some computers that can measure analog signals. For instance, the radar, when you are in ship, there's this thing that is turning around, that is checking whether there's an enemy coming, it will detect it,
Yeah,
because
sure.
it's a continuous signal. There's nothing like, okay, let us leave this second. So in that case now when you come to digital computer, now you look at this, like the chart there. Voltage, right, is continuous flowing, but we cannot continue measuring. Look at, so just that short that short time, I can measure voltage five billion times. Does it make any sense? It doesn't make any sense now. If I measure voltage 5 billion times, I'm going to get a particular value for voltage 5 billion times. But why would I? Just like temperature. If I can measure it every 1 second, okay, why do you think I should measure it 30 times every second? So that 1 second is assumed to be a representation. So that's what we call digital. Then when we talk about hybrid, which is your question, hybrid, whenever you hear hybrid, is a combination of both analog and digital. Okay, hybrid computers have features of both analog and digital computer. Okay, it is fast like an analog computer and has memory and accuracy like a digital computer. So it is combining both. For instance, something that is measuring like a concentration, CO2 concentration in the air, for a human being to understand it, it has to represent it in a digital way. If he measures in analog and put the output in analog, oh boy, I'm going to see ones and zero, tiny, tiny, tiny numbers in it. It's not going to make any sense. But somehow it's going to digitize. That system can digitize it. That's what is hybrid. Hybrid is combination of the power of what? The analog and the power of the digital. But the computer, as you know it today, okay, is digital computers. Okay, you're going to
Oh,
see when we go further, when I begin to break down the bits, what is even called bits, what is called bytes. You're going to understand. I'm going to talk about bits and bytes tomorrow, combination of ASCII, Unicode, digital to analog converter. I'm going to talk about all those ones tomorrow. But hybrid,
all
to
right. Thank
answer
you,
your
sir.
question, is combination of analog and digital. Thank you.
Now I understand now. Just like when you have hybrid cows.
Thank you. Hybrid of well and God bless you,
Yes.
CNG and all that. Thank you. Yeah.
Uh,
Yeah.
thank you. I appreciate it.
All right.
Okay. Thank you very much. Okay, I think that's all for today. So yeah, the video will be uploaded on YouTube. So I think I've dropped the link to our YouTube channel, right? Do well to subscribe to our YouTube channel so that once we upload the video, you will just be notified on your device, whether it's your mobile device or your laptop, right? Or your desktop or whatever it is you're using, right? So please yeah, so we continue tomorrow, right? Same time. So first session is going to be the learning management system, the LMS, and the Discord onboarding, right, for CodeCamp, and then of course, then the DIPOD session by 2 p.m. Right. Ms. Lawrence, if you're speaking, we can't hear you.
Okay, sorry.
Yeah, I can
Can
hear
you
you
hear me
now.
now?
Yes.
Okay, so I please I think let me use this opportunity to tell those on the call. I would have said it earlier. You still have opportunity of bringing in your friends. What we're doing all this is to make sure everybody's onboarded before the actual, track classes commences next week. You still have from now to weekend. See, you can see the energy I used to teach this class, I can equally use it to teach 10,000 people. Nigeria, we should know these things, you understand? Nobody should like, we should be the, like, in the next, our goal is like, we should be in this tech thing with confidence and we should be world stars. No, like this thing I'm talking about now, go and check it anywhere in the world. Okay. It is, in fact, before you get it, what I did is a combination. You can say I do biology, history, and everything. It's because I took time. So why not bring in your friends, talk about it, also the track is going to be like this as well because it's a game changer. We're actually very passionate about making this country, making this country the hub of tech in Africa. So that's where we are going. I know it's a big dream, but well, you can always start from somewhere. So I just want to mention it. They have opportunity of registering. They have till now, so they have from now till Monday and all that. So I think in all these sessions this week, you understand, we should keep on like making people come into this thing because it's only once in a year. And we are not going to hear that for the guy. This one I've thought now. No, but even if they come in, you have to go and watch it because it takes a lot of energy and all that. So, all right. Thank you. Just want to
Okay.
mention that.
Yeah, thank you very much. Yeah, so still let's try to see if we can get people to register, right? It's a free training. So yeah, it's free. So let's see, invite your friends. Registration will actually close very soon. I think maybe by Friday or Monday we'll actually shut down registrations, right? So um let's get that. So I'm seeing questions about tests and all that tomorrow, right? Tomorrow we will handle every question you have that has to do with the boot camp, right, will be handled tomorrow. So every challenge also that you're having will be handled tomorrow by 12 p.m. Right. So let's just yeah. So thank you very much, everyone. And I'll see you all tomorrow, same time, same link, like I said, same link. And then finally, for those of you who are saying they haven't received a mail, if you registered on or before Wednesday last week, please check your mail again. Check your spam folder also, right? Mails were sent to over 2,000 persons. Okay. And from our records, not up to that, not up to half or more than half of that number has actually viewed that mail. So it has actually been sent. So check your spam folder, except you registered from Wednesday down, last week Wednesday down, mails will be sent in the next one at the next 1 hour maximum. So please do well to check your spam folder, check your inbox. And if you haven't received another round of emails will be sent. Um, but if you're also on the Discord, you don't really have much to worry about. Check your mail. And I also hope that you what's it called? Um, I also hope that the email you put is actually a valid mail, right? But I think it should be, of course. So thank you very much, everyone, and have a wonderful day ahead. Bye. See you tomorrow.